Good morning, students. In today's class, I am going to teach you about perception, space, depth, and distance. So, let us begin with our class. The visual field or surface in which things exist, move, or can be placed is called space. Okay, the space that we live in is organized in three dimensions. We perceive not only the special attributes, that is size, shape, direction of various objects, but also the distance between the objects found in the space. While the images of objects projected onto our retina are flat and two-dimensional, that is left, right, up and down, we still perceive three dimensions in the space. Why does it happen so? It occurs due to our ability to transfer a two-dimensional retinal vision into a three-dimensional perception. The process of viewing the world in three dimensions is called distance or depth perception. Although the images of objects projected onto our retina, when it goes to our retina, it is flat and two-dimensional, but still we see the world in three-dimensional. Okay, we not only see the size, shape, and direction of an object, but we also can perceive the depth or distance of a particular object. Suppose we see two people on the street, we will come to know that which one is closer and which one is further. If someone is shouting at us, if two people are shouting at us, we will know that which one is shouting from a closer distance and which one is shouting from a more distant place. We come to know about the depth perception. Okay, the distance between these objects. Okay, and it is known as depth perception. So depth perception is important in our daily life. So for example, when we drive, we use depth to assess the distance of an approaching automobile, or when we decide to call a person walking down the street, we determine the loudness with which to call. Okay, we determine loudness also on the basis of depth perception. In perceiving depth, we depend on two main sources of information called cues. The way we determine depth, okay, the way we perceive depth, we depend on certain cues. So there are two types of cues to determine this depth. One is your binocular cues, which requires both eyes, that is the function of both the eyes. Another one is your monocular cues, which require the function of only one eye. A number of such cues are to change a two-dimensional image into a three-dimensional perception. Okay, so first let us look at the monocular cues, which is also known as your psychological cues. And your monocular cues of depth perception requires only one eye. Okay, so let us start with monocular cues. Monocular cues of depth perception are effective when the objects are viewed with only one eye. These cues are often used by artists to induce depth in two-dimensional paintings. There are paintings which are two-dimensional, so artists use these cues to induce depth. When you see paintings, then it looks very real, right? So you have to use these cues in order to make the painting very real. Some important monocular cues that help us in judging the distance and depth in two-dimensional surfaces are described below. So we will be talking about these cues now, okay, which requires the function of only one eye. The number one is your relative size. So the size of retinal image allows us to judge distance between our past and present experience with similar objects. As the objects get away, the retinal image becomes smaller and smaller. We tend to perceive an object further away when it appears small, and closer when it appears bigger. Okay, so So this is a very common and it's easy to understand. So as the objects get away, the retinal image becomes smaller and smaller. So uh, you must have noticed, suppose if you are traveling or if you are walking, and then uh, your friend is standing and then you are further away, then the image of your friend is going to be smaller and smaller. It will become smaller. We tend to perceive an object further away when it appears small and closer when it appears big. So if something looks big, then it feels like it is closer to you, okay? And if something is relatively small in size, then we feel like it is further away, okay? So if you see, suppose two mountains, one is big in size and the other one is small in size, from a distance, then you will feel as if the bigger mountain is closer to you and the smaller mountain is further away from you. But that may not be the case, and maybe the smaller mountain is nearer to you than the bigger mountain. But since the bigger mountain is big in size, it may feel like that is nearer to you, okay? So that happens. Then comes your interposition or overlapping. These cues occur when some portion of the object is covered by another object. The overlapped object is considered further away, whereas the object that covers it appears nearer. Okay, so just think about two objects, okay, one on another. The overlapped object is considered further away. So the one which is behind is considered further away, whereas the object that covers it appears nearer. So the covering appears that it feels like that is nearer, okay? So just try to think of some example, like put two objects, overlap it with each other, so the cover, the one which is in top, will feel like that it is nearer, okay? Now comes your linear perspective. This reflects a phenomenon by which distant objects appear to be closer together than the nearer objects. For example, parallel lines such as rail tracks then appear to converge with increasing distance with vanishing point at horizon. The more the lines converge, the further away they appear. So now think about railway tracks. If you have been in trains, then think about these railway tracks, okay? Keep this image in your mind. So they appear to converge with increasing distance with a vanishing point at the horizon. Just think about a railway track line and just think about the image. The more the lines converge, the further away they appear, okay? So the more they converge, the further away they appear. I'm also attaching a video at the end of the slide so that you understand the linear perspective better, okay? So now let us talk about aerial perspective. So the air contains microscopic particles of dust and moisture that make distant objects look hazy or blurry. This effect is called aerial perspective. For example, distant mountains appear blue due to the scattering of blue light in the atmosphere, whereas the same mountains are perceived to be closer when the atmosphere is clear. Okay, so this example, if you notice, okay, on a cloudy day, when there is dust, particle, moisture, then you see the mountains, then you will feel like that they are further away. But on a very clear sunny day, when everything is clear, you will feel like the mountains are closer. This happens. I'm sure that as a child you must have observed these things. I remember as a child I used to ask my parents that, yesterday I felt the mountains were further away and today I feel like they are so close. So this happens, okay? So this happens because of the microscopic particles of dust and moistures that make distant objects look hazy or blurry, and because it looks hazy and blurry, so it looks more distant. But on a clear sunny day, it will look like that if it like it is closer to you, okay? Now comes your light and shade. So in the light, some parts of the object get highlighted, whereas some parts become darker. So highlights and shadows provide us with information about an object's distance. So just think about any house or any tree, some part is highlighted and some part is shadowed. So that also helps us to know the depth of that particular object, okay, where it is, how far it is, or how near it is, okay. Highlights and shadows also helps us in knowing the distance and depth of a particular object. Then comes your relative height. So larger objects are perceived as being closer to the viewer and smaller objects as being further away. When we expect two objects to be the same size and they are not, the larger of the two will appear closer and the smaller will appear further away. So I have already talked about this thing, that larger objects are perceived being closer to the viewer and smaller objects as being further away. So if you place two things at the same distance, but one is bigger than the other one, then you will feel like the bigger one is nearer to you and the smaller one is further away, okay. So the larger of the two will appear closer and the smaller will appear further away. Then comes your texture gradient. So it represents a phenomenon by which the visual field having more density of elements is seen further away. In figure 5.15, the density of stones increases as we look further away, okay. So yeah, so here it feels like that the density, okay, it represents a phenomenon by which the visual field having more density of elements is seen further away. So the more density the element has, it feels like that it is more further away, okay. So you can imagine things which has more density, and then you will notice that the more density it has, it looks further away. So in the picture 5.15, it seems like that the density of stone increases as we look further away. So it looks like the bricks, okay, at a distance are very close, okay. Maybe when you are looking at the first part of the picture, it doesn't look that dense, okay, but if you look further away, it looks like there are many bricks together and they have no space in between them. So the density looks a lot, it looks, the bricks looks very close to each other, but in the beginning it doesn't look that close, okay. After that comes your motion parallax. So it is a kinetic monocular cue and hence not considered as a pictorial cue. It occurs when objects at different distances move at a different relative speed, okay. So it occurs when objects at different distances move at a different relative speed. So the distant objects appear to move slowly than the objects that are close. So what happens is that the objects are very close to the window. Suppose you are in a bus, okay, then the objects very close to the window, such as small trees planted by the highway, seems to rush by you, if you have noticed. And beyond the small trees you can see a distant house or something, okay. And that doesn't move very quickly, but the nearer objects, they seem to move very quickly. Like imagine you are on a bus, okay, and then it seems like the nearer trees will rush by very fast, but at a distance, at a distance, if there is a house or a mountain, then it will move slowly, okay. So that happens in your motion parallax cue, okay. Now let us talk about binocular cues. So this requires the function of both the eyes, okay. So we have to have a three-dimensional space which are provided by both the eyes. So there are three of them, three binocular cues. So let us look at them. So the number one is retinal or binocular disparity. Retinal disparity occurs because the two eyes have different locations in our head. They are separated from each other horizontally by a distance of about 6.5 centimeters. Because of this distance, the image formed on the retina of each eye of the same object is slightly different. This difference between the two images is called retinal disparity. The brain interprets a large retinal disparity to mean a close object and a small retinal disparity to mean a distant object, as the disparity is less for distant objects and more for the near object. Okay, so see, our retina are not located at the same position. We have two eyes, so two retinas. Okay, so and they are located in different locations in our head, and they are also separated by a distance of about 6.5 centimeters. So because of this distance of 6.5 centimeters, the image formed on the retina of each eye of the same object is slightly different. So if you are seeing a cup, okay, with both of your eyes, so both the eyes are not going to form the same image of the cup. It is going to be a bit different because they are located 6.5 centimeters apart from each other. So this difference between the two images is called retinal disparity. Okay, so with both your eyes, you are looking at a cup, and both your eyes are forming two different images of the same cup. So that difference between the two images of the cup is known as retinal disparity, and the brain interprets a large retinal disparity to mean a close object and a small retinal disparity to mean a distant object, as the disparity is less for distant object and more for the near object. So if I am placing a cup near me, and if I am looking at a tree which is further away, so the tree which is further away will have less retinal disparity than a cup which is near to my eyes. Okay, so the further the object is, the lesser the retinal disparity. The nearer the object is, the more the retinal disparity. Okay, so after that comes your convergence. So when we see a nearby object, our eyes converge in order to bring the image on the fovea of each eye. A group of muscles send messages to the brain regarding the degree to which eyes are turning inward, and these messages are interpreted as cues to the perception of depth. The degree of convergence decreases as the object moves further away from the observer. You can experience convergence by holding a finger in front of your nose and slowly bringing it closer. The more your eyes turn inward or converge, the nearer the object appears in space. So you can try that. Okay, just put one of your fingers in front of your eyes and try to bring it near to your eyes. Okay, so what will happen is that the more your eyes turn inward or converge, as in like both the eyes, the more it will converge. What conversion is. If they both come closer to each other, the more they are coming inward, the closer the object appears in space. Okay, so try doing this experiment with other objects also. So just hold probably a pen or anything. Okay, the closer it comes, your eyes are going to converge more or are going to get inward more. Okay, and the closer the object in space will appear. Okay, so the more it converges or comes inward, your eyes, the distance of the object appears to be closer to you. Okay, so try experimenting. Then comes your accommodation. So accommodation refers to a process by which we focus the image on the retina with the help of ciliary muscles. Okay, So these muscles change the thickness of the lens of the eye. If the object gets away more than 2 meters, the muscle is relaxed. As the object moves nearer, the muscle contracts and the thickness of the lens increases. The signal about the degree of contraction of the muscle is sent to the brain, which provides the cue for the distance. So see, now think about a camera lens. Also, a camera lens also does the same thing. Okay, so what happens in accommodation? So in this process, we focus the image on the retina with the help of ciliary muscles. So we have ciliary muscles in our eyes. Okay, so with the help of our ciliary muscles, we focus on a particular image on the retina. Suppose you are looking at a pen in your table. Okay, so we focus on the pen, and we focus the image on the retina with the help of our ciliary muscles in the eyes. So these muscles change the thickness of the lens of the eye. Okay, so we have lens in our eyes. Okay, so these ciliary muscles change the thickness of the lens in our eyes. Okay, so now if I move that pen, okay, it was near to me, but I move the pen, someone moves that pen and it gets away more than 2 meters, the muscle is relaxed. Okay, so our muscles will get relaxed. So as the object moves nearer, the muscle contracts and the thickness of the lens increases. So the nearer the object is, the muscle becomes thicker. Okay, sorry, the muscle contracts and the lens becomes thicker. Okay, and if the object is nearer, and the further it is, if it is further away, then our muscles relax, it doesn't contract, it relaxes, and the thickness of the lens also becomes lesser. Okay, if you take the example of a camera only. Okay, so the nearer the object is, we have to put more focus on it. Okay, the lens becomes thicker. So with our eyes also the same thing happens. So the closer the object is, the ciliary muscles of the eyes, it contracts and the lens becomes thicker if the object is nearer. If the object is moved further away, then what happens, the muscles, it relaxes, it doesn't contract, and the lens becomes thinner, it's not thick anymore. Okay, so remember that the signal about the degree of contraction of the muscle is sent to the brain, which provides the cue for distance. So if you have noticed that if an object is closer to you, then there is more pressure on your eyes, if you have noticed. Okay, so this happens because the muscle contracts and the lens thickens. And when the object is further away, then you will notice, you try doing this, you will notice that your eyes will relax. That does happen. So try this by doing it on your own. Okay, so this is all for today's class, and I will be attaching one video in the next slide. Please go through this, and if you have any doubt or confusion, you can ask me.